So next we're going to look at 8.6 parametric equations, graphs, and applications. Let's start by understanding how to graph a plane curve defined parametrically. So basically a parametric curve is a xy curve in the Cartesian coordinate system that occurs over time. And so time is represented by t, and here we are actually looking at an interval of time from -3 to 3. And over time, the values of x and y are generated according to these two formulas. So what you want to do is, step one, you want to make a table of corresponding values of t, x, and y over the domain of t. So in the case of -3 to 3, we would want to use nice numbers from -3 to 3. And then we're going to fill in the values of x and the values of y simply using these two equations. So this is what it would look like to fill in the values of x. You plug in -3 squared minus 1 is 8, etc. Then you're going to fill in your values of y in the same way. So -3 minus 2 is -5. And then step 2 is simply to graph those values. So you would graph the point 8, -5, 3, -4, 0, -3. All of these are x, y points, just like you used to graph back in Algebra 1. Here's the result. Now, which of these is the first point? The first point that happens at the very beginning of the time interval is 8, -5. And the very last point that occurs is 8, -1. So this is the first point, and then this is the last point. Now really there shouldn't be arrowheads here if my domain is limited from -3 to +3, then I'm going to be generating this curve. And you can see that at time 0 you are at the point -1, -2, which is right here. So we're starting down here at -3 and we're going all the way here to +3. So if we got rid of the arrowheads, which give us the illusion that the time is going to continue to go in both directions, then this finite interval would be our full graph, and we are moving in a certain direction. We're moving from this bottom point to the top point as time progresses. So now let's look at my open math question number 18. So how do we graph right here? Well, what we want to do is we want to start with making an xy table that includes t. So that would be a txy table. And we're going to start with -1, and then we're going to move to values greater than or equal to -1. So if I start with -1 and I plug it into the x equation, I get -1 squared, which is +1, plus 2 times -1, which ends up being -1. Then I plug in -1 here, and I get -1 plus 1, which is 0. Now the y values are going to be nice. You just add 1 to each of the t values, so those are very easy to fill in. The x values, though, are a little more complicated, so we have to square and then we have to add 2 times the value. Here we still get 0, though. And then we get 1 plus 2, which is 3. 4 plus 4, which is 8, and 9 plus 6, which is 15. Now looking at this graph, I'm not going to be able to fit all of these x, y points. I've got the point -1, 0, and I have the point 0, 1. Those will fit. Then I have the point 3, 2. That's going to fit. But when I get to 8, 3, it's not. So if I'm looking at -1, 0, I'm at right here. And then 0, 1, I'm at the point right here. And then 3, 2, I'm up here. Then I'm going to go to 8, 3, which is way out here somewhere. What I'm going to be seeing, though, is it looks like a square root equation or something. Doesn't that remind you of a square root equation? So I would pick this graph right here, the one that looks like a square root equation. Okay, so what we're going to do is we're going to pick the square root, and we're going to start at -1, and then we're going to put our second dot here at +1, and that is going to be our graph. Now we know that the graph is going to move from left to right, and we know that from our graph, from our table, because our values started here and then they moved in this direction. So our table tells us that we're moving from left to right, even if the graph, we can't tell that by looking at the graph. We can only tell that by looking at the table itself. So next we want to consider how to find an equivalent rectangular equation for a parametrically defined curve. So if you were to have x is equal to t squared minus 1 and y is equal to t minus 2, and you're in the interval t -3 to 3, what you could do is you could eliminate the parameter t by solving either equation for t. Of the two, this second equation is a whole lot easier to solve for t. And once you solve for t, then you do a substitution. You replace the t in the first equation with y plus 2, and then you simplify. And you can see here a parabola. So now let's look at homework 24, number 19. We want to start by getting t by itself in one of the two equations. Of the two, the second is easier to work with. So we would end up subtracting 3 from both sides, and then we'll divide both sides by 5, and that will tell us that our t value is y minus 3 over 5. So now we're going to replace, in this other equation, we'll go ahead and replace t with y minus 3 over 5. And now, so that it will look like a rectangular equation in a more standard form, we're going to go ahead and square both sides. Don't forget to put parentheses here. And so then the result is x squared is equal to, this would be a 49, and then this is y minus 3 over 5. Okay, so you would want to then multiply both sides by 5 over 49. Multiplying both sides by 5 over 49, you end up with y minus 3 is equal to 5 over 49 x squared, and then you would want to add 3 to both sides. So you have y by itself. And that's it. Now what is shown here for MyOpenMath is algebraically equivalent. Instead of 5 over 49, they've written 5 times x over 7 quantity squared, which you can see would become 5 over 49 x squared. If you were to write it in this format or the format I wrote, either way, we would have y as a function of x. So now let's look at how to graph another type of curve. We have x is equal to 4 cosine t and y is equal to 2 sine t. So what we want to notice is that x is equal to 4 cosine t is the same thing as cosine t is equal to x over 4. And y is equal to 2 sine t is the same thing as sine t is equal to y over 2. Now, since sine squared plus cosine squared is equal to 1, what we want to do is write this as cosines. We're going to substitute for sine t y over 2, so we have y over 2 squared. And for cosine t, we're going to substitute x over 4, so that's x over 4 squared is equal to 1. And that's the same thing if we rearrange that as x squared over 16 plus y squared over 4. And the reason we're rearranging that is because we have a major axis and a minor axis of the ellipse. So we have an ellipse centered at the origin and the endpoints of the ellipse, given that the major axis is going to be 4, and we have the minor at 2. These are the endpoints of the ellipse, and this would be the graph. So now I'll work out page 403, number 16 on the board. Okay, so let's start by looking at the x and the y. What we want to do is get sine t and cosine t each by themselves. And we're going to do that to be able to use the Pythagorean identity. Since we know that sine squared plus cosine squared is equal to 1, we can replace sine of t with x over root 5 and cosine of t with y over root 3. And now we have x squared over 5 plus y squared over 3 is equal to 1, which is an ellipse centered at the origin. Now the square root of 5 is just a little bit beyond 2, so we're going to have points on the x-axis at square root of 5, 0, and negative square root of 5, 0. And then points on the y-axis at 0, root 3, and 0, negative root 3. This is standard for graphing the ellipse. And now we connect the dots. But we're still dealing with a parametric equation. So what does a parametric equation have to do with all this? What we have done here is actually part B. We started with part B because it's a lot easier to graph this curve if we start with part B. And that is to rewrite what we had written as a parametrically defined curve in as a rectangular equation. But we want to consider the fact that the parametric part of the problem shows that this is happening over time. So if we were to look at the very beginning point, where is the beginning point? When t is equal to 0. So if you plug in 0 for t back in these original statements, then you have that the sine of 0, which is equal to 0, right, is equal to x over root 5. So then we could say that our first point is going to have an x-coordinate of 0, because the sine of 0 is 0. Okay, and then let's consider the second value here. We know that the cosine of 0 is 1. So if we're looking at the cosine of 0, and that is then equal to y over root 3, that would mean that the y-coordinate is going to be the square root of 3. So our very first point on this curve is 0, root 3. And where is 0, root 3? It's right here. So at time 0, we're actually going to start at the top of the ellipse right here. And then as time progresses, let's look at which direction we're going. If we were to plug in pi halves, for instance, when you plug in pi halves, that's where you're going to get a value of 1, right? So that's when your x value would equal root 5. So that means that at pi halves, I'm going to be coming over here. At time pi half, I'm over here. So the orientation of the graph is that at time 0, you're right here, and then you're going to come down here to this part of the ellipse at time pi halves. And then at time pi, you're going to be going around here. We're going clockwise. Down here at the bottom of the ellipse would be at time pi, and then we're going to continue around clockwise. This point way over here occurs at time 3 pi halves, and then we keep going around. So this going around happens to be in clockwise. We're starting at the very top here. We're only going around once though, because our interval is from 0 to 2 pi, and we can see that we get through a quarter of the ellipse for each quarter of the interval. So that's the meaning of the parametric equation part. Parametric equation takes what a plain old rectangular graph, which you usually look at as just one picture on a piece of paper with no motion. And the parametric part of the equation allows us to see that there is actually motion that's occurring over time, and that it's following this particular path. It's almost like the difference between the racetrack itself versus the horses on the racetrack running their race. So next let's look at number 21. Just as I did on the board, I want to start by isolating cosine and sine, which would give me cosine of t is equal to x plus 2 and sine of t is equal to y minus 3. Now we're going to use that Pythagorean identity. Cosine squared t plus sine squared t is equal to 1, and now we do substitution. And then what do we have here? We have a circle. The circle has a center at -2, 3, and we have a radius, I'll call that c for center, and then the radius is the square root of 1, or 1. So if we go to find -2, 3, right here, my circle has to be 1 above, 1 below, 1 to the left, and 1 to the right of the center. So the circle is going to occur right here. Now, what is the orientation of the graph? Where do we start? Well, at time equals 0, we can go ahead and plug in 0 now for cosine and sine, and let's see what that would look like. So the cosine of 0, of course, is 1. Cosine of 0 happens at x plus 2, so that means that x is equal to -1 at t equals 0. So at time equals 0, the coordinate that we're starting at, our starting point is -1, 3. So -1, 3 is right here. This is where we're going to be starting. Okay, and then our next point we're going to look at is what would happen at t equals pi halves. So if we were to replace 0 now with pi halves, the cosine at pi halves is 0. So that means that the x value now would be at -2. So at t is equal to pi halves, you're going to have a x coordinate at -2. So it could be either one of these two dots. So I'm going to keep going. Let me plug in pi halves over here now. The sine value at pi halves is 1, so that means the y value is 4. So at t equals pi halves, I'm going to be at the point -2, 4. So if I start here, and then I move up this way, that would mean that I have a counterclockwise motion. I'm going around the circle once. Here is time 0, pi halves, pi, 3 pi halves, and back again to 2 pi. And so that would be a counterclockwise orientation for this graph. So where we really see the application of parametric equations is with projectiles, flight, that kind of thing. So here, if we were to look at a toy rocket is launched from the ground at a velocity of 30 feet per second at an angle of 45 degrees with the ground. Find the rectangular equation that models this path, and what type of path does the rocket follow. Okay, so the way that we can do this is there are already parametric equations defined for gravity on planet Earth. And they are, x is equal to v naught, the initial velocity, times cosine theta t, and then y is equal to v naught, again the initial velocity, sine theta t, minus 16 t squared. Here's to account for gravity over time. And so since we know 36 is the initial velocity and the angle is 45 degrees, then we can replace every occurrence of cosine 45 and sine 45 with root 2 over 2. So that would mean that the x would simplify to 18 root 2 times t. And you could also write that as t is equal to x over 18 root 2. And then y would simplify to 18 root 2 t minus 16 t squared. Now the reason that we're writing it like this is for the sake of substitution. But what you would really want to say that the parametric equations that you have for your horizontal and your vertical component for this projectile are x is equal to 18 root 2t would be the first one, and then the second one is that y is equal to 18 root 2t minus 16t squared. But we're going to go ahead and solve for t so that we can do a substitution, and then this would actually allow us to see the shape of the rocket, which should not be surprising that it would be a parabola. So here's that substitution, and then when you simplify that further, you can see that you get x minus 2 over 81x squared, and that would be a parabolic path. And I've just now written it as y equals because they should include y. Okay, so next, now I want to look at MyOpen Math. So for number 22, we're not dealing with a projectile. We're talking about an object that's moving on a straight line path. Now, when we talk about straight line, you should think y equals mx plus b. And that's exactly what we're going to do, except we have an x equation and a y equation. So when we're looking at x of t and y of t, instead of calling them each mx plus b, that would be a little confusing to be using the same variable twice to mean two different things in an equation, in the same problem. So instead of mx plus b, and we don't want to use x again, we're going to say, I'll say a t plus b. That's kind of the mx plus b format, except instead of x we're using t because this is a function of t. And so I don't use a and b again. Over here I'll say c times t plus d. So this still follows the same y equals mx plus b format that you know from Algebra 1, but we're using t as our variable and a and b as the constants that I need to fill in. Now I know that at time equals 0, the value of x at time equals 0 is -9. So if x of 0 is -9, that means that the b value for this first equation would be -9. And similarly, you can do the exact same thing for y, and you can figure out that the d value then is 9. So now we can rewrite these equations, and we now just need to figure out what a and c are. So I said the b value was -9, and I said that this d value was +9. And now we want to look at time equals 1, so we're going to replace t this time with 1. And at time 1, the x value is -1. And at time 1, the y value is 3. So then I have a minus 9 and c plus 9. So then that tells me that my a value is equal to +8, and my c value is equal to -6. So for my x, I'm going to write 8t minus 9. And then for my y, I'm going to write negative 6t plus 9. And then you can double check. You're going to take the times 0. If you plug in times 0, here you get an x value of negative 9. Plug in 0, here you get a y value of positive 9. That matches this. And then plug in 1 and you get negative 1. Plug in 1, here you get positive 3, and that matches this. So you can double check in the end that when you plug in the time of 0 and you plug in the time of 1, you should get the 2 points that you were looking for. Now, when I had shown you the x and y equations before for gravity, instead of 4.9, we had the number 16 here, and that is because when I showed you this example here uses feet for gravity. All right, so acceleration due to gravity is 32 feet per second squared, and this would always be half of gravity. But if you look back now at my open math, we're looking at meters per second squared, and gravity for meters per second squared is 9.8 meters per second squared. So when you half the number 9.8, you get 4.9 right here. So it's going to be the same equation that we used for the slides, except that this value here needs to be 4.9. So to get the x part of the parametric equation, we replace v naught with 450, that's this right here, and then we're replacing alpha with pi thirds, so cosine of pi thirds, and then you still have the t hanging around. So now we have x is equal to 450 times 1/2 t, so we can simplify that to x is equal to 225t. And likewise for the y value, we have y is equal to 450 sine of pi thirds t minus 1/2, 9.8 t squared. So what we want to do is to simplify that further. Since the sine of pi thirds is root 3 over 2, we end up with root 3 over 2 times 450, which simplifies to 225 root 3 times t. And then, of course, I already said that 1/2 times 9.8 is 4.9. So when will the bullet hit the ground? The bullet will hit the ground when the y component of the height, so that's the height, is 0. So if we replace y with 0, and then we would factor out the t, and then if by the 0 factor property there will be two values where the height would be equal to 0, and the first would be at time equals 0. This would be when the bullet starts. This has no initial height whatsoever, and so then the other location would be, rather the other time, not location, is going to be 225 root 3 over 4.9, which is approximately 80 if we round to the nearest second. So we are going to round to the nearest second here with 80, but we want to use an unrounded value for the next part so that we don't create a rounding error. So notice here that it's 79.5329, and you can even use the value in your calculator, which goes out even further. So you would say that the value here is going to be 80 seconds for your answer, but then you're going to use this unrounded value. Now this next part is how far from the gun will the bullet hit the ground? And for that, how far would be the horizontal component. So the vertical component, the y value, tells you the height. And then the how far is the horizontal component. So what we're going to do is we want to replace the t in the x equation. Remember the x equation was 225 times t. So we're going to replace the t with the value from the calculator ideally. Although this is 4 decimal places out, which is completely sufficient for us. And that is going to be approximately 17, okay, it's this value right here, 17,895 meters, and that would be rounded to the nearest meter. Now, if you had used 80 instead of this decimal point, you would have got 80 times 225, which is 18,000, and you would have then been off by over 100 meters. So that's why you don't want to use a rounded value for a later part of the problem. So then lastly, what we have here is question 24. A drone traveling horizontally at 80 meters per second over flat ground at an elevation of 4,500 meters must drop an emergency package on a target on the ground. The trajectory of the package is given. We already have the equations given to us, so we don't have to create them like we did back in number 23. Where the origin is the point on the ground directly beneath the drone at the moment of release. How many horizontal meters before the target should the package be released in order to hit the target? So this question might sound intimidating, but it's really not bad. What you want to do first of all is just figure out how long is it going to take for the package to hit the ground. And so that would be take this y component and set y equal to 0. Okay, so then after this we want to solve for t using the square root property. And so the t value here, it turns out to be about 30 seconds. Now, we don't want to use the about 30 seconds. We want to use this value as we are using the x component part of the problem next. X is equal to 80 times that value. So x is then going to be equal to 80 times square root of 4,500 over 4.9. And then when you approximate that, when you round to the nearest meter at that point, then you end up with 2,424. So you don't want to round until after you've put the exact value in, and then that would be the nearest meter for your answer. And that's 8.6, and that is the very last lesson that we are learning from the textbook. So congratulations for making it this far.